My name is Vlad. I'm a rock musician from Kiev, Ukraine. I'm really happy to be here. I'm always looking for excuses to visit Prague because I think it's one of the most beautiful cities in the world. Thank you for coming. I want to talk about vector maps and what Mapbox is up to today. I'm working for a company called Mapbox. We're building the future of interactive maps. And what you need to know about Mapbox is that it's an open source first company. And that pretty much 100% of code I wrote in the last 5 years working at the company is open source. Well, maybe 99%. And I'm also known for building a small and really simple JavaScript library called Leaflet. And first, before going to talk about vector maps, I want to give you some historical context of how we got to this point and what's the fuss about vector maps. So 11 years ago, I started working for a mapping startup called CloudMate, and this was a company that was building business around OpenStreetMap, a free map database of the world. And I was really excited about working with maps. I knew absolutely nothing about maps. I never had any formal GIS education or anything, so they invite me to those mapping and GIS conferences often, and most of the time I have no clue what people are talking about. And I actually got into web development because I needed to build a website for my band. Still continuing to write code for 15 years now. And also we released one of the most beautiful albums in Europe in the last years. And it's hard to be a musician in Ukraine, so I have to advertise my music at tech events. 2008, I was really young, I was naive, I was a university dropout. So I thought, hey, I'm doing maps now, so how hard could it be? It must be simple. Maps are something really, really easy. I thought that, maps it's just a bunch of square images, right? Nothing more to it. Just a bunch of square pictures, and you kind of want to drag them with the mouse to see some other places. And you maybe want to put some icons on top. And basically that's it. That's everything I knew about maps back at that time. So I thought, oh, that's easy. I was full of enthusiasm and I decided, hey, I will build my own JavaScript mapping library. It should be a few hundred lines of code. Right, and my company, my manager said to me, hey, we'll give you the task of building our mapping API, and you need to use established, mature, open source solutions. I said, hey, no, I want to write my own JavaScript library. It will be great, I promise you. And he said, no, we can't risk building something from scratch. It's really complicated. We need to use established open source solutions. And at that time, I had to start learning more about maps. And I started seeing all those weird terms I knew absolutely nothing about. The only open source established solution at the time was OpenLayers, and back in 2008 it was a really, really scary piece of software. And creating a web map back at the time was looking like this. So this OpenLayers thing, it had 200,000 lines of code. 200,000. It had like 1 megabyte of JavaScript, and it's completely fine in 2019, but not in 2008. Back then, it was a huge deal having a megabyte of JavaScript on your page. So I get really scared, and I didn't understand why. Like, why are maps so complicated? It shouldn't be that way. Yeah, I first tried to build some kind of wrapper around this open source solution, but I felt that it worked really not well. And then I went to share my idea with the community. I went to some like online chat about OpenStreetMap and mapping and said, "Hey guys, I want to build this new cool, very lightweight JavaScript library for maps. What do you think?" And I was told, "No, you're an idiot. You can't do it. You will waste your time. It's really hard. You'd better just start contributing to existing projects and not spread yourself thin." So I thought, challenge accepted. And I started writing. So I had a deadline, like in a few weeks, I had to present my new JavaScript API to the management. And the management said that I need to build it on top of OpenLayers. But I decided to still write my own library, and I didn't tell anyone. Well, I was a bit silly, but yeah, I started writing code, and I thought, oh, maybe if it doesn't work out, I'll code something quick in one night and present that. So a few weeks passes, deadline comes, and I'm presenting our first version of the API. It was called Web Maps Lite back then. It looked like this. And the management tried to use it. They dragged the map around and they, why is this map working so fast? And they couldn't understand. They never saw any like web maps working fast and smooth. It was always having some lags, and it was not a pleasant experience to work with maps in 2008. So at that point, I had to admit that this is not an OpenLayers-based wrapper. It's something I built from scratch, and that's why it works so fast. And the management was so impressed by this then that they decided, okay, continue building this thing. It's cool. So I continued working on it, and 3 years later, we released it as an open source library called Leaflet. And basically, Leaflet was born again as a protest against bloat, clutter, and complexity, because I had this idea that maps should be something very simple and accessible and easy to use. And now Leaflet is pretty much everywhere. It's an industry standard. You can, if you see an online map somewhere, chances are that it's probably Leaflet. For example, if you're opening a map on Facebook or Foursquare or Pinterest, GitHub, all kinds of visualizations online, and even my favorite map of Skyrim. So Leaflet is now the #1 mapping library in the world. And that's all because that I didn't know shit about maps. and I wrote it with my own perspective. I think if I got any like serious GIS academic education, I would never write something like Leaflet, because all this weight of knowledge would push me off the path of building something simple. So Leaflet is still really great. It's extremely lightweight and simple. It's very easy to get started. It has a really huge community and like hundreds and hundreds of plugins. It's stable as a mountain, and it works practically everywhere. Even in Internet Explorer 8, no one cares about Internet Explorer 8, but Leaflet works on it pretty well. So, and up till this point, I talked about the so-called raster tiles era. Raster tiles era is the era, it's how web maps work usually. So the biggest followers or implementers of the raster tiles era are Google Maps, OpenLayers, and Leaflet. And the status quo of web maps, like how they usually work today, if you see them on some web page, is that maps are used as a background, mostly static, like nothing happens on the map. It's always top-down, oriented north. You can't rotate the map. It has a rigid set of zoom levels. So zoom level 0, zoom level 1, zoom level 2, and you can't do anything in between. The data is loaded only on those set of levels. There may be some simple vectors, icons on top, but you can't easily build like interactive experiences with like thousands of objects because it will be too slow. And conceptually, raster maps are the same as they were 14 years ago when Google Maps API were released for the first time. So 5 years ago, I joined my dream job. I joined Mapbox because I thought that Mapbox shared my vision of building mapping tools that are easy and simple and accessible and fast and awesome to use. And by the way, this is one of the earliest logos of Mapbox. So Mapbox was really stressing on the fact that it's not GIS, because GIS is something not very good association. So Mapbox vision for maps is creating living, breathing, rich and powerful mapping experiences that make you feel connected to the world. And games did it for decades. Why can't we do something like more interactive, more interesting with maps? So let's take a look at the evolution of the Elder Scrolls games. In 2002, Morrowind, it was absolutely beautiful. In 2006, Oblivion, beautiful. 2011, Skyrim, also absolutely beautiful. Now let's look at the evolution of web maps. The same years, 2002, there were no web maps, and they were super ugly images usually. 2006, we already had Google Maps API, and 2011, we got Leaflet. So yeah, compared to what we could do with like graphics cards, with games, it's just not really fun. So and raster web maps didn't change much after 2011. Now there's also this thing that the world of technology is rapidly changing, and now we're in the era of mobile phones, and technology shifts to be mobile-centric rather than like web-centric. So digital maps before were exclusively web technology, and now digital maps are native mobile apps and web too, but native mobile apps first. So browsers before in 2008, they were good at displaying a bunch of text and images. They were not good at rendering anything interesting. And browsers now, you can do anything. You can render anything. Anything is possible basically. So we decided that vector maps are the future because we wanted to build something more interesting with maps. Yeah, and we decided, oh, let's build a vector maps platform from scratch. How hard could it be? This sums up a lot of our experience building a vector maps platform. And some of the early screenshots of working on vector maps, pretty trippy. Yeah, so now we're coming to the so-called vector maps era. And actually, all the big players in the mapping industry, they entered the vector maps era already, whether you realize it or not, because some of them only entered it on the mobile phone, like, for example, Apple Maps or Google Maps, the application, the end-user application on the web, it's already vector maps based. It uses WebGL, and of course, it's vector maps on mobile. Esri here, Carto, Mapbox, of course, Yandex Maps, Maps.me, all of those work on vector maps. So, what are vector maps, and why are they so much better than raster maps? So the first thing that you'll notice when you try to use a vector map is how smooth and nice it is to use simply. Just exploring the map feels so much more natural because you don't have those abrupt changes between round zoom levels. You can explore the map however you want. You can rotate it, you can pitch it, and you can zoom smoothly to any point, and all the labels, all the data will be crisp at any of those points. So yeah, this is possible because we don't have, you can see the lines change smoothly. So the line width transitions smoothly as you zoom in. The labels, so there are no abrupt changes. And it makes using the map much easier. Then there are 3D features. For example, an oblique view that you often see on navigational maps in the car. 3D buildings, which are very useful sometimes. This is an example of an indoor map. It becomes much nicer with 3D. And another really powerful thing about vector maps is that you have full control over data presentation in real time, because we load the raw data from the server, and then we can style it however we want in real time on the client. So this is a bit of a contrived example, but you can see that the style transitions smoothly between like day style and night style. So you can change anything about the appearance of the map in real time. You can change colors, you can change line widths, you can change anything. So you can change maps based on the context of their usage. This example, you have to kind of look closer to see what's going on here. But this is a relief map, and the lightning always stays from the top left side. So you could never do that with raster maps. And it feels so much more natural this way, because this shading is happening on the client based on the relief data in real time. And another big point is that any object on the map can be interactive. So with raster maps, you had this map background, the base map, and you could not do anything with it. And with vector maps, you can hover over any object, you can click on any object, you can make anything interactive, any road, any building. And it starts with some simple examples like this horopath, and it can get more interesting, like this example with like hovering over a building and doing navigation to it. And data-driven styling means you can join data associated with certain geographical features with these features and visualize them in real time as well. So this visualization uses the third dimension to demonstrate the scope of something. I don't know. Yeah, and so those kinds of visualizations can be quite pretty. And there's also a point of performance. Performance with raster maps like leaflet, you can render maybe a few thousand objects. It will be okay, and then it will start lagging. With vector maps, you can render basically hundreds of thousands of features with millions of points. So here's an example. On this map, I'm loading a 100 megabyte GeoJSON file on the client. So no server involved. I just dropped the GeoJSON file, and it loaded it, and it displays it smoothly on any zoom level, and you can explore it in real time. So, and this is an example of a heat map, a dynamic heat map so this is a dynamic heat map of 400,000 points. I think this was never possible before. So you can do really highly interactive and really fast experiences on huge amounts of data with vector maps. And what all this like powerful interactivity and flexibility also enabled is a visual map editor, something that was not really easily done before. So Mapbox Studio is an application where you can style your map and your data in real time, like change colors, add layers, change any aspect of the map, and it will just reflect immediately on the map. And this is a very powerful tool, and you can create some really powerful map designs with it. Here are some examples of things created in Mapbox Studio. Some really pretty ones. And also going back to performance, vector tiles use many times less bandwidth than raster tiles, especially now that most screens are like double resolution, like Retina display, and corresponding raster images are of much bigger size than a corresponding vector tile, as you can see on this chart. And there's also a point to make of simulation and cartography, and like our goal behind the Mapbox GL project. So this is a screenshot from Google Earth, and there are similar projects like Cesium.js and Melon from Prague, by the way, which try to simulate the world or make a technology to see the world as you would see it from the bird's eye. And it can be really cool for some applications, but Mapbox focuses on a completely different aspect, on cartography. And cartography doesn't need to show you the world as it looks. It shows you the world so that you can understand it easily. And it uses symbols and colors for that. So it doesn't look like it looks from the bird's eye view, but you can understand it much better. And this is cartography, and this is what Mapbox GL focuses on. So it doesn't have as much of sophisticated 3D features as some of the other libraries like Cesium have, but it just focuses on a different thing. Now, everything behind this client-side rendering is open source. The main repository for the web client is Mapbox GL.js on GitHub, and there's also Mapbox GL native, which is the implementation of the same vector maps technology for all the native platforms: iOS, Android, Qt, Node, OS X, Linux, Windows, your refrigerator, anything. And it's written in C++, and those two implementations, they are developed in parallel. So one code base in JavaScript, another code base in C++. And each code base is fully optimized for the platforms it's supposed to. And you might think, oh, why didn't we see more WebGL-based maps before? And why Mapbox had such a hard time building it? So WebGL is currently supported pretty much everywhere, on every major browser. And you don't have to worry about compatibility at all, it just works. So there are not many WebGL applications today on different websites, not because it's of the bad compatibility. Compatibility is perfect. It's really, really, really good. So the real reason why there are not many WebGL applications is this one. So this is building a WebGL application. Turns out that building WebGL applications and libraries is really, really, really hard. And there's a common misconception that OpenGL or WebGL is like a 3D API. So you tell it like, draw me this cool 3D model, or draw me this cube or sphere with this lightning. And actually, OpenGL is a really low-level, really basic 2D API. And everything it's really good at is basically drawing triangles. So we can rephrase that as OpenGL is a technology for drawing triangles really, really fast with your video card. So there are some abstractions on the JavaScript land for building 3D applications that like abstract all the complexity away and that know how to turn what you want to draw into triangles, like 3JS or Babylon.js or Pixie.js. But they are general purpose libraries, and they're good for like small 3D scenes, but not good for scalable map rendering, because map rendering is really hard, and you have to draw like millions of features 60 times per second, and you have to optimize it as much as as possible. So you have to write everything from scratch. So let's look at an example of how you draw lines in OpenGL or WebGL. So maybe many of you are familiar with the Canvas API, the Canvas 2D API, where you say just move to this point and draw a line to this point in this color with this width. It doesn't work like that in OpenGL. It has some really basic primitives for drawing lines, but they're mostly for debug, not for display, because they're really, really ugly. So to draw lines so that they display beautifully, you have to consider something called anti-aliasing. It's smoothing out the edges around lines. So here's an example of how you can draw a segment of a line in WebGL. You draw two triangles for the middle part. you draw two triangles for one side because you need this kind of gradient to make this anti-aliasing, and another two triangles. So 6 triangles for one line segment. But we can do better than that, because the more triangles we use, the worse it performs. And WebGL and OpenGL support adding arbitrary attributes to vertices. And we can use that to do some cool math, saving so-called normals at every point. And then we can render a line segment with 2 triangles, which is a huge progress because it's 3 times faster. But this is just one segment, and you have to consider, for nice polylines, nice roads, you have to consider line joins. There can be several types of line joins. There can be meter, there can be round line join, bevel. So how do you draw this round, nice line join at every point? Of course, you draw it with triangles, more triangles. So drawing-wise is really hard. But drawing-wise is extremely easy compared to drawing polygons. As you guessed right, if we have a polygon with some holes maybe, to draw it, we just have to split the polygon into triangles. And turns out that this is a really, really hard problem. And I spent months on it to build a fast enough solution, because the existing ones were too slow and too unstable, and they broke on many types of data. So I wrote a library called earcut. It's also open source, of course. It was ported to C++ too. And it does this kind of triangulation or tessellation, or breaking down polygons into triangles really, really fast. And at times I had nightmares at night about triangles. It was, yeah, it was difficult to develop this thing, but it kind of works. And now we come to drawing text. And you might have guessed, drawing text is not easy in OpenGL. So drawing text. We can't directly say, hey, draw me this hello world in this font, like you do in Canvas 2D. You have to draw triangles. And to draw triangles for text, you draw 2 triangles for each letter, and you use a part of a texture to draw the specific shape. So we need to generate special images called font textures with every combination, every kind of character that we may use on a map. And we use that texture as kind of a sprite to draw every letter. But this would be too easy. Because you have to consider that when you zoom the map or rotate it, you have to also zoom the labels or rotate the labels, or maybe draw halos around them, and then you can just render all the characters into one image, because if you rotate it, it will have ugly artifacts, and you can't easily increase its size because it will look blurry and pixelated. And by the way, we have a special font server that serves those kinds of font textures. So when you load the map, it calculates which characters you use, and then it loads Unicode intervals corresponding to those characters with those textures. But to make it possible to render the text nicely with rotation and scaling and halo, we have to use the technology called signed distance fields. This is a technology that was made popular by a company called Valve when developing Half-Life. And it allows encoding vector data in a raster way, and then displaying it with sharp edges. So textures look kind of blurry like this because every pixel encodes the distance to the real edge. And you can reconstruct the actual vector with pretty good precision from this texture at many scales, and it doesn't get blurry when you increase the size. So the font textures look kind of like this. And here's a debug page showing how those textures look for different fonts, because every font in Mapbox GL has its own texture. And when we load all those textures, we have to create those kinds of images and pack them as closely as possible, as efficiently as possible, because WebGL has limitations on how big of a texture you can use. So if you go past, for example, 2048 by 2048, it may crash. So we have to pack as efficiently as possible. This is a library we wrote called PodPack that does this really fast and really efficiently. Like, it takes arbitrary sizes of rectangles and squares and packs them into one square layout. And it's useful not only for maps and textures, it's useful for building sprites for web development, for example. But this approach of loading textures becomes not very good when you try to explore the map in China or Japan or Korea, because they have thousands of different, many thousands of different characters. If you try to load this much on the map, for example, you browse to the Chinese map, and there are all kinds of labels, and it tries to load 10 megabytes of those font textures. And it's, of course, too much data to load, and it's especially too much if you consider trying to use this map inside of China, because due to the Great Firewall, the internet is not so fast there. So you can wait for 2 minutes for map labels to load. So I built this library called TinySDF, which generates those font textures on the fly. So it uses Canvas 2D API first to render like crisp characters and kind of turns them into like vector ones. But that's not all about text. There's also this problem of drawing some languages like Arabic, because in our like in European languages or English, it's simple. If you have a text and you have a picture for every character, you can just put this character alongside each other, and the label will be nice. In Arabic, different kinds of symbols, if they are close together, they turn into a completely different symbol. So it's really tricky. So we couldn't implement the algorithms to properly do that in JavaScript. It was too hard of a problem. So we got this IQ for C library, a hardcore library that has like 20-year history and is really complicated. And we compiled it with mscript into JavaScript and created a plugin for displaying Arabic text properly in WebGL maps called Mapbox GL RTL text, right to left text. And maybe we'll do a WebAssembly version too. So, but this is just rendering text. And placing labels is a whole different kind of problem. Because when you have those fluid maps, you have to consider rotation, and you don't want those labels to ever overlap with each other so that everything is clear. And you also want those labels to be crisp at all times, and you can notice that labels that go along the road, they kind of like follow the shape of the road, and you have to account for that. And everything happens in real time. It's a really, really complicated part of the Mapbox GL stack. I think maybe 50% of complexity is related to font rendering and placing labels. So this is the debug view of the label system with boxes and circles that we use for collision detection. So we get these boxes and circles together in a spatial index, special data structures that are very fast to search. And then we kind of collide everything with everything and see what labels to display. I really love spatial indices, so I wrote 6 different libraries for them. Although we don't use any of the ones listed, we built a custom one based on a grid. But yeah, it's really complicated. Then there's this task of loading and processing data. In vector maps, data is loading similar to raster maps, so it loads it tile-based, but tiles are bigger, and they are not images, they are vector tiles. So they are binary files with all the geometries and feature properties encoded into the file. And to do this decoding from vector tiles really fast on the client, we of course had to write our own client libraries because it wasn't fast enough to use official libraries. JavaScript is called PBF, and on C++ side we have Proto0, which are the fastest decoders of protocol buffers. So protocol buffers is the binary format that we used for encoding this vector tile data. And protocol buffers are great because they are much smaller than JSON would be, and they are much faster to decode. So we're loading binary data instead of JSON, which is more common on the web. And to describe the schema of how exactly we encode geometry and property features into protocol buffers, we keep an open specification called vector tile spec, which describes in really great detail how to do that. And this specification got adopted by other big players. So in addition to us using vector tiles, PostGIS implemented vector tile support, and Esri is using vector tiles for the vector maps too. The same specification. Then there's the problem of, okay, on the server we can generate this vector tile data and spend as much time as we want, but what do you do if you try to load big GeoJSON file on the client, like I demonstrated earlier? So we needed a really fast library for slicing arbitrary geodata into vector tiles on the client, so directly in the browser, in the JavaScript version, and in C++ too. So we built this library called GeoJSON-VT, and it does this really, really fast, and it's also now used not only in Mapbox GL, it has other useful use cases where you have to like simplify and break down big parts, big geodata. Then we have this cool feature called clustering, which is basically the only good way to display a huge amount of points on the map, or generalize points on the map. If you have 1 million points to display, clustering groups points that are close together into objects. And to do that really fast on the client, we of course built our own libraries, supercluster and supercluster HPP. The supercluster can be used with leaflet, by the way, and also display millions of points. Then there's this fun task of finding where to put a label on a polygon, because if you calculate the centroid, it can be outside the polygon. So I came up with this fun algorithm called polylabel, which does this really fast and finds the point which has as much space as possible around it to place a label. And we also use it in Mapbox GL. And then there's this problem that if we tried to directly load all this huge amounts of vector data on the main thread in the browser and try to process it and do all those heavy computations like breaking things into triangles, it would be an unbearable experience because every time you do intensive computation in JavaScript, it freezes the browser completely. You can't click on anything, you can't do anything with the web page. It just freezes. So for that, there was a new feature by browsers called web workers, and we use that extensively to load all the data in different threads, process it as much as possible off the main thread, and quickly transfer the ownership of this data to render on the main thread. And we can't even transfer like this data nicely in JSON because it's too slow and the amount of data is too big. We have to turn this data into binary and then transfer it to the main thread. And this is also a separate problem. But we do it. And I mentioned that we have two parallel implementations of vector tiles. One is for the web, written in JavaScript, and another one is for C++ and a host of our other languages for bindings to various native platforms. And we need to make sure that our maps display absolutely the same, whether it's a mobile phone or a web page. So we have a pretty advanced continuous testing system that runs tests and checks whether every property of the style specification or so the same data with the same specification of how to render it renders exactly the same on native platforms and on the web. And currently we have more than 1,000 so-called render tests to make sure that everything stays the same and we don't regress anywhere on the two platforms. Oh, and of course, to compare the screenshots, we wrote our own library called Pixel Match because we needed a way to compare screenshots, taking into consideration small differences in anti-aliasing between platforms. Because if you render something on Linux and then try to render something on Windows, it will have slightly different rendering that's imperceptible maybe to the eye, but it will still trigger the difference when trying to measure it computatively. So we wrote a library that kind of tried to measure the difference using human perception of color and detecting anti-aliasing areas to exclude them from comparison. And we tested on continuous integration servers. Every commit of every repository runs through all these thousands of tests on every platform, like Linux, like iOS, everywhere. Yeah, and so far I only talked about what happens on the client side. What's there on the server side? I don't have time to talk about that today. Sorry. So, yeah, we worked really, really hard to bring this technology to the world. But the essence of software engineering stays the same. It's mitigation of complexity, turning something that was hard and complex into something that's easy to use for developers, so that you don't have to think about all these problems. You can just write, display me a map, this beautiful map with those points, and it will just do that. So compared to Leaflet, Mapbox GL is vastly bigger in scope, much harder to develop, but it has the same goal of letting people build amazing maps. Yeah, that's it for today for me. Thank you.